Ну, нормально, да, вот я себе.
Да, что это тоже разложите это
Свидетели вполне нормально. А? Не, новый какой-то вообще не.
Вот явное разложение, движение массы. Вот надо сделать вот такое. Раз, вот это будет
Hi. Oops.
And our next speaker is Professor Ji Wu. So please welcome.
Okay, so thanks for the organizers. Okay, it's my pleasure to give a presentation in this nice meeting. Now, oh, I should share screens, right? Okay, let me do this. So now, yeah. Is it okay now?
Yes, okay.
Yeah.
Okay, we can.
Okay.
We
Is it okay now?
Yeah, yes.
Okay.
Okay, we can.
Okay, so now. Okay. How is it now? The work? Oops. Okay, so should I start? Angie? It's okay? Oh, okay. So, so my talk here is try to give present some top algebraic topology method in knot theory. So I think nowadays, people like to do possible, interdisciplinary collaborations, right? Now, so I think I presented a few ideas we can see use some algebraic methods to look at some knot theory. Okay. Well, let me start from this. So actually, this idea is not really a new idea. So it's actually let me see the backwards the first one. So if you're back to the history, I think everybody knows Vassiliev, right? And if you look at how Vassiliev introduced his invariance, right? So if you look at the Vassiliev invariance, well, actually he already used algebraic topology. So rather than the standard method in low dimension topology. Okay? So you look at the space of knots, okay? So space along knots actually studied by Vassiliev, then produce the Vassiliev invariant. Okay. Now, there have been a lot of work on this, right? So on the space of the knots, okay. So you can look at the space of knots and look at the cohomology. In my impression, Vassiliev is the first person to study this topic. Okay. Then there are a lot of people follow up to look at further on this Vassiliev invariance, right? So if you look at the there's some, well, this will be slightly more recent paper, right? This is already publishing book about the Vassiliev invariance, how to look at the space of knots. Okay. Now the also I can search a bit on some reference, right? In 90s, so these I think should be Toshitaki Kono. There's a misprint here. So Toshitaki Kono has been trying to look at the Vassiliev and from some way to study the geometry, right? So you look at the time complex of the space of knots. Now, and we can find more people try to make applications of the knot space, right? So in physics. And if you think about this space of knots, actually, it will be naturally connected to algebraic topology. Actually, there's an operator theory. It's pretty connected to that one. Okay, so it's a. So I think that you can see I just put some title of paper here. Now also there'll be some recent work. I just select a few, right, to look at the space of knots. And if you look at the follow-up work of Vasiliev, there will be a lot of connection with algebraic topology. Okay. So now let me put a bit away. So the idea to use algebraic topology method, as I said, is not a new idea. Okay, Vasiliev already did it in a very good way. Now we just put a bit new idea here. So try to look at the combinatorial topology to look at the knot invariance in certain other ways. So I think recently people have been trying to look at the knot invariance different from some given say polynomial other values. You can give some graph value knot invariance or some elements in groups, right? So here we try to think about some kind of knot invariance which is theoretically constructed, right? So the idea we can say, okay, we propose the following way. So let's do something connect to algebra topology. So if given knot, okay, so we can assign something as a knot invariance, right? So let's try to assign something which has a nature of in algebraic topology, like space, right? And also have some combinatorial information, right? And also try to get some group in, structure there. And then this canonical one actually is so-called the simplicial groups. Okay. So simplicial groups will, in some sense, is a combinatorial model for loop spaces. So the idea here, we try to say, okay, given knot, can we just make a simplicial group? Okay. Well, we'll see. It is possible. Okay. So now let's see how the simplicial group is supposed to be. Well, the story for simplicial group in algebraic topology, actually, in the contents of algebraic topology, you can backwards to 1950s. So the first game is a generalization of a simplicial complex, so which is the simplicial set. Briefly speaking, we consider some degenerate simplexes. For example, if you consider, say, one simplex with vertex labeled by 0, 1, then we can consider this as a degenerate two simplex in two ways. So we consider as a two simplex 0, 0, 1 or 0, 1, 1, right? So just double the vertices and make us area to be 0, like two simplex. So in such a way, we can make some notion of a so-called the originally so-called semi-simplicial complex, later on was called the simplicial set. So a kind of a combinatorial model of a CW complex structures. So all here, the XM, you can think about set of n simplexes. And the phase will be indication. So if you get two simplex, you have 3 possible phases. So this makes that a function. And degeneracies, as I said, you can make doubling on vertices. So you go up to as a kind of like degenerate or pseudo higher simplex. Now then make a system. Now a good point of this simplicial set is that one can do homotopy theory. Okay, so simplicial complex it's a good model for homology theory, but if you do homotopy theory, even Cartesian product of simplicial complex, you have to do some triangulation. So, but if you put in the setting as a simplicial set, everything will go to as a category will be straightforward. So homotopy theory will be canonically introduced, and this notion, as I mentioned, is in 1950. So given by Ellenberg, Zilber. Now, the notion of a simplicial group is actually a straightforward extension of a simplicial set. So you just replace each set as a group, and each phase and the degenesis just a group homomorphisms. That's all. Okay. So this will be as I just put a few remarks that it is quite known, well known in algebra topology that the category homotopy category of simplest set is equivalent to homotopy category of CW complexes, and the homotopy category of a simplicial group is equivalent to homotopy category loop spaces of CW complexes. Okay, so now the geometric realization of a simplicial group is actually a topological group. Now here's a I think this is a work by the work of Anders Milner in publishing Anders in 1957. Okay, so he has put a condition like if this group or if a simplicial set has a locally finite or countable element, then the geometric realization of a Cartesian product simplicial set is really Cartesian product of space. Okay. Now, if you, of course, you can extend the Milner's result that if you put the compactly generated topology, then the Cartesian product simplicial set, geometric realization of Cartesian product simplicial set is the same as a Cartesian product of the space, and by taking compact generated topology. Okay, so in such a way, then every simplicial group, because the multiplication will become to continue, so it's give a topological group. Now, so this is I give an impression that in algebra topology, actually, when we say simplicial group, you really talk about space, right? Loop space. Now, if you can do the classified space, then you backwards to any space you want. Okay, so now so now let's see back to here. So back to our question. So this will be some kind of like a curious question. So we try to locate. So let's try to make some crazy idea. So make something like give a knot. Can we make a knot invariance to using like this kind of notion of simplicial group, right? Well, this is possible, and one way is like this. So the construction looks like pretty naive. Okay, so that's why we call naive cabling here. So you look at here. So the one condition is that we need to put a frame on the, well, in general can be linked, right? This machine works for links. Now, if you want to look at the knot, you just look at it as a knot. Now, so you need some kind of like normal vectors, right? Vector field, normal vector field, to as a frame to put on that. Now, then what the frame used in the construction? Well, once you have a normal vector, let's say the knotting go this way, the frame goes that direction, right? Along the frame, then you can take a parallel one. Okay, just everything push the frame, and so you start with say a knot or link, and put L0, just say this one. Okay, then you try to doubling it, just parallel. So that's why we need to make a choice, choose a frame. So because just make parallel one. Okay, so this is what we call a naive cabling. Okay, so you get the, if you start with a knot, when you doubling that, you get the two component link, right? And then you try to one more time, and so far and so on. So the way we try to observation is that if you put this system as a sequence, okay, so what do we get? So we start with a knot, you get say a sequence of links, right? Okay, so just like systematically, and then you just take group. Okay, so just take group. So the starting one, the first one you take group, you just say not group or link group. That's the game you start. Now the second one, the group will be a changer, right? Because you take the naive cabling. So actually you start with a knot, you get a two component link, and then you take a group of them. Okay, and so on and so on. Now the observation is that if you do this way, there's a canonical way, simplicial group structure there. So you can observe what's going on. If I put the M, so my label N is from 0 up to 0, 1 to M. So if I think about the nth term, okay, so this think about the elements inside here as n simplexes. Now the canonical way to produce phase operation. So you look at these vertices, or think about vertices labeled by 0, 1, 2, up to n. Okay, so you just draw like pictures, simplex. Now, canonical way to produce phase just delete the one vertices, right? So you delete 0, you get one phase opposite. Then delete 1, and so on and so on. So you get canonical phase operation, and which are group homomorphism, no problem, because you just remove it, one component. And then you can see the observe that you want to produce a simplicial, so you need to create something degenerate operations, right? Well, it is also given in a canonical way. So you think about, as I start in the example, to say that if we want to think about one simplex, say 0, 1, as a two simplex, there are two ways. One is 0, 0, 1. Another one is 0, 1, 1. So in other words, you can double the first vertex, double the second one. Now, if you draw intuitively, you can see that if I have a double, say M is exactly, I can double I string. So I just put in the middle, parallel one. So that's why this normal vector field helps a lot to construction. So we don't want to say curved around, just put parallel one. So in this way, we will really get a simplicial group. Okay. So now the question will be, okay, so now let's see, you do that. Okay. So now what's the question we can see? Well, there will be, I think it will be kind of interesting. So let's ask the first question. So what is the, you get a simplicial group, it says that it is a loop space, right? So it is a loop space of what? So first question will be, you get some kind of simplicial group. As I should mention that traditionally people construct simplicial group in algebra topology using free group or free product. So only recently we try to look at it like using geometric groups to construct the simplicial group models for hoping to get some informations on the homotopy from the low density topology. So this actually is a new type of simplicial group, right? Which are given by link group. And now the answer will be, here's the theorem. Okay, so the answer is that if you take the geometric realization, it will give actually it's a wedge of the 3 spheres. Okay, let's see. So how can you count the number of the wedge of sphere? How many components you have? So if you start with a link, okay, so you take a splitting decomposition. So each of these each of the sublink will be maximum non-splittable components, right? So you just put the pattern here, and then remove those trivial fringed links. So trivial here means a trivial knot together with trivial fring. Okay, so forget those guys, and then the remaining pieces, say you say up to k. Okay, so the remaining, so these are non-trivials. So okay, so up to k, and from k plus 1 to p, say, are trivials. Okay, so forget those trivial components, and then that's the counting here. So how many copies of 3 sphere you put here, and you get loop space. In other words, if you start with a knot, okay, let's say you start with a knot. So there's only one choice. So there's only one answer. So if this is a non-trivial fring knot, so that means either a knot is non-trivial or the fring knot is trivial, but the fring is not trivial, like Hopf. You will create like Hopf links. Okay. So in this, if it's non-trivial, then we'll get a model of a loop S3. If it is trivial, then you get a contractible. Okay, so the answer actually. So let's our result actually we found the connections between the algebraic topology and the knot theory. So if you proceed in that way. Okay, so now how many? So I have still a few minutes. Okay. So here's I already mentioned. So actually the work will be this one. If you look at the homotopy type, actually the homotopy type of such kind of construction only tells the for knots either loop S3 or trivial. So you won't distinct the like two knots if you look at the homotopy type. Okay, but if you look at the isomorphism type, that will be quite different, right? Even because the fundamental group will start with knot group, so it's already tells a lot. So it's a very lot of structures in there. But if you simply look at the homotopy type, that's two-way in some sense. Only gives like tells you when it is trivial. Okay, so now of course I put some few questions because this is the work we done, and I think we try to work further. So for example, I list a few questions. Say if you I think for knot groups, there are some questions try to look at the homomorphisms between knot groups, right? If you look at the fringed knots, actually, these homomorphisms will be actually create the simplicial homomorphism because everything is constructed in a very natural way. So there's some geometric construction. Geometric again means here simplicial structure. So you can see something in algebraic topology, you can put it here to study simplicial homomorphisms. And if you you can try to look at the homotopy theory here. Don't look at the homotopy group. Homotopy group only depends on homotopy type. That's two-way. But if you take a stronger, you take whole group modular boundaries, in some sense, just do homotopy directly in the group, then there'll be a lot of non-trivial information can try to be explored. Okay, so there are some more. So you have some simplicial group on hand. Actually, you can look at the homology of representations of knots. Basically, you can produce. Okay, every representation will create some homological information. So this should give some different type of possible knot invariance you can construct. Okay. Now, since because of timing, so I mentioned a bit there are some other explorations to see. So this story I try to look at is actually about the intersection of the subgroups, right? And this is actually a big story on the group theory. It's not a simple question how to understand the intersection of two subgroups, right? And the one work I want to mention here is about the Brownian links. Okay, so there's one question we have been looking at. Okay, I skip the Brownian links, as I assume everybody knows. Okay, one question we try to look at the Brownian, because the Brownian links, the group of Brownian links actually is pretty strong. In some sense, they can determine the link in some way. Okay, so now you can look at some subgroup. Okay, so intersection subgroup. And this intersection subgroup actually we can answer out for Brownian link. And the answer will be this intersection is exactly equal to the symmetric commutator subgroup. So let me explain a bit of symmetric commutator. So first of all, you take R1 is the normal closure of the first meridian. R2 is normal closure of second meridian, so on and so on. Okay. So these are intersection of the normal closure of meridians here. So you take the first two, so take commutator, then you take the R3, okay, so third commutator again, subgroup again, and until M, then I put the S here, that means you can permute the indexes, okay, or permute the index, or possible, then take the product. So it is clear that this group is always contained in the intersection because these are given by the normal subgroups. But another way is actually not simple. And I want to mention this one because we actually, the proof of this one is used with quite homotopy theory. So you need some so-called cubical diagram to try to determine the higher homotopy group can be represented into fundamental groups. There are several works we did before, and then try to work out that. So I'm not sure how can we easily to work out use method of low dimension topology, but somehow the home table theory method is quite works very well for this question. Okay. Yeah, I think that's basically what I try to share my views on the algebraic topology methods in knot theory. As I mentioned, actually there's a lot of way to look at the knot theory from algebraic topology, right? Starting from Basiliv. So here where we just say from a little bit from the construction of a simplicial way and some cubical diagram. The second one is a cubical diagram. Take home to be co-limit, then you get some result in knot theory. Okay. Well, the last slide, so I try to say that actually the talk, because we try to make it possible, right, in the interdisciplinary study, right? So I need to mention actually possibly knot theory can go further, not just like interdisciplinary study within topology, right? We can go out to biology. Well, there's one traditional connection with biology is the protein and the DNA structure, right? These backbones given by knots. And then recently there's a lot of games used by algebra topology. It's used so-called topological data analysis, right? So if not theory plus this algebra topology, you will see that there's something catch the backbones and together with some data analysis, possibly we can get some more information out of that, right? Okay, yeah, I should finish my talk here. Okay.
So please questions. There's some questions online, Zoom. That's all. Okay, thank you very much again.
Yeah, thank you. Yeah.
We continue in 10 minutes. And next speaker will be what kind of thing.
Okay. Okay, yes.
Okay, thank you very much.
Yeah, thank you. Oh, I see Valerie is here, right?
Yes.
Yes.
How are you? How is your?
Good. And you? Yes. You see, I'm at home, so there's a better way. You put it. You cannot do in the classroom, right? Do you see this one?
Yes.
I can start here. Right?
Ну что, ну не знаю, сумма значения Сам один еще один.
Да.
Вот. Потом сформулировалась гипотеза.
Интересно.
И чтобы как-то вот а вот они куда он конечно не может быть моделям, где есть где есть какие-то веса, которые не очень
Я написал,
Коллеги, мы через минуту продолжим.
Я просто
Нет, спасибо, нет.
Мы включены читать? Dear colleagues, let us continue our session, and our next speaker is Mahendra Singh. Are you here?
Yes, I am here.
Okay,
Hello.
nice to see you. Nice to see you. Okay, welcome. So please.
Thank you. So let me first thank the organizers for giving me this opportunity to present some small observations that we made. So yeah, I forgot to write here. So this is a joint work with Valerie Bardako. So these are this is a new topic that I've been trying to learn, and there are some very basic observations. So let us start moving. Yeah. So what is a Yang-Baxter equation? So let V be a vector space and R from V tensor V to V tensor V a linear map. Then we say that R is a solution of the Yang-Baxter equation if this identity holds as morphisms from V tensor V to itself. So what is this? So you have R from V tensor V to itself, and you just tensor it with the identity on the third coordinate, right? So that is what this R tensor ID stand for, and similarly ID is identity tensor R and so on. So we have this equation, and you see this resembles the braid equation. So if I set R tensor identity as just for convenience R12 and identity tensor R as R23, then I can write the preceding equation as R12. So here the product is composition, that's understood. So R23, R12 is same as R23, R12, R23. So which is a braid equation. And this equation is called the Yang-Baxter equation. So there is another related equation, what is called the quantum Yang-Baxter equation, and how does it really differ from the preceding one? So you have this identity, so that the R12 composed with R13 composed with R23 is same as the same written in the reverse order. Okay, and this equation appeared in quantum mechanics and other areas of physics. So maybe I will just make a comment later on. So so how are these equations related? Solutions to these equations related. So if you look at T from V tensor V to itself, the flip map, which sends X tensor Y to Y tensor X, then one can easily see that R is a solution of the quantum Yang-Baxter equation if and only if R composed with T is a solution of the Yang-Baxter equation. Okay, so Yang-Baxter equation is which gives you the braid equation. So that's how we should remember it. And since this T is invertible, so therefore there is a bijective correspondence between solutions of the quantum Yang-Baxter equation and solutions of the Yang-Baxter equation. So therefore one can very well just concentrate on Yang-Baxter equations because it looks closer to mathematics since there is a braid equation. So this flip map is an obvious solution of the Yang-Baxter equation, as we can see. So just to from the historical point of view, so these equations appeared in the works of C.N. Yang on many problems and R.J. Baxter on vertex models. So I will not really say much about this. I'm not really an expert on this, but they have a really deep connection with physical phenomena. Okay, so what is a set theoretic solution of the Yang-Baxter equation? It is a pair XR where X is a non-empty set and R is a map from X cross X to X cross X such that this equation holds. So R times identity composed with identity times R composed with R times identity is same as the role of the two operators interchange, identity times R composed with R times identity composed with identity times R. Okay. So this is a set theoretic solution. As we can see that now tensor product has been replaced with the Cartesian product, a little easy to handle. So what is the relation here? So if X is a basis for a vector space V, then a set theoretic solution of the Yang-Baxter equation will give you a solution of the Yang-Baxter equation. So therefore one can very well just concentrate on set theoretic solutions. And this is what the problem proposed by Vladimir Drinfeld in his very popular, I think it's a survey article, Unsolved Problems in Quantum Group Theory, and where he proposed to find, classify all set theoretic solutions of the Yang-Baxter equation in an approach to find all solutions of the Yang-Baxter equation. So this question has really attracted a lot of attention from mathematicians, so particularly because of the braid equation appearing there. And last decade has really seen a lot of progress in this. So I will say a couple of things about that. So let us look at some solutions, at least some non-trivial solutions. So obviously the flip map is a solution that we know. And look at this map, second example. So from integers cross integers to itself, if you look at this map, one can check that it's a solution of the set theoretic solution of the Yang-Baxter equation. And if you take a group and you define this, the solution R as this map R of xy equals to y comma y x y inverse, and take another example as R of xy equals to xy inverse x inverse and xy square, then one can easily check that these are solutions, set theoretic solutions of the Yang-Baxter equations. Okay. So these groups, you can say integers also group. And fourth example is if you take a permutation of a set and you set R of xy as sigma y, sigma inverse x, it's also a solution. And another example is, which is more relevant to knot theory, is if you take a quandle. So what is a quandle? Quandle is, you can, third example, the first case in the third example is an example of a quandle. So it's a set with a binary operation that has certain axioms, which are just algebraic formulation of the three Rademacher moves. Okay, so there is an idempotency axiom, and right in this case, my convention suggests that left multiplication is a bijection and left distributivity. So if X is a quandle and you set R of xy as y comma y star x, one can check that this is also a solution of the Yang-Baxter equation. So there are a lot of these interesting algebraic structures which are appearing in the as solutions of set theoretic solutions of the Yang-Baxter equations. So therefore, it becomes interesting to classify these algebraic structures themselves to say more about the solutions. And I'm going to talk about a specific type of solutions called cycle sets, which we'll talk about later. So here is an interesting connection with braid groups, as one could have guessed. So if XR is an invertible set theoretic solution of the Yang-Baxter equation, and let's say Bn denote the braid group on n strands. So if I set Ri plus 1 as this map from n-fold Cartesian product of X to itself, where Ri comma I plus 1 is, which is identity on the first I minus 1 components and identity on the n minus I plus 1 last n minus I minus 1 components, and as R on the I and I plus 1 components, then this map sigma I go to Ri plus 1 is a representation of the braid group. So set theoretic solutions also gives you representations of braid groups. So I will not dwell more into this. So as I said, so an approach to find and classify the set theoretic solutions of the Yang-Baxter equation is to try to understand and classify these algebraic structures which give rise to such solutions. So to proceed further, let me set some notations. So suppose R is a map from two-fold Cartesian product of a set to itself. So I can write this map Rxy as sigma xy tau yx, okay, just for convenience. Then we say that R is a non-degenerate. If R is a solution, then we say it's a non-degenerate solution if these maps sigma x and tau y as map from x to itself are invertible maps for each x and y. Okay. In case if only one of them is invertible, say for example sigma x, then we say it's left non-degenerate, and if only tau y's are invertible, then we say it's right non-degenerate. So there are examples of solutions which are only left non-degenerate, which are only right non-degenerate, and so on. And a solution is involutive if the square of this map is identity on the two-fold Cartesian product. So with this terminology, Wolfram Rump in his advances paper in 2005, he introduced these objects called cycle sets. So let us see the definition. So a cycle set, I'm saying left here because you can put a right analog of this, and also there are two-sided analogs which are more cumbersome to define, so I will not go into that. So a left cycle set is a non-empty set with a binary operation, such that with this operation, the left multiplication by each element is a bijection, and this identity holds. Okay, so x dot y dot x dot z is same as the same equation with role of x and y being interchanged. And a cycle set is non-degenerate if the squaring map from x to itself, which take a to a dot a, is bijective. So how are they related to solutions of the Yang-Baxter equation? So before going there, let me just tell you at least some examples. So the most interesting example here is a rack. So a rack is again so racks is a set with a binary operation which satisfy such that the left multiplication by each element is a bijection, and it satisfies the left distributivity axiom. So not racks are complete. Racks also give invariant for framed links. So that is how it connects with knot theory. And if a rack is such that is group of inner automorphisms. So inner automorphisms is simply the group which is generated by left multiplications in my case. If that group is abelian, then this is a cycle set. So there is a fair reasonable supply of these algebraic systems. And for example, take another example. Take this as x as z union with a additional point. And if you set this binary operation as this, that each integer just act as identity, and the infinity just shifts an integer and fixes infinity, then this is a cycle set. In fact, it's a non-degenerate cycle set, and the first one is a degenerate one. So there are plenty of examples, and this, one can actually find more. So what Rump proved is the following result. So non-degenerate cycle sets are in bijection with non-degenerate involutive set theoretic solutions of the Yang-Baxter equation. Okay, so recall a right cycle set is non-degenerate if the squaring map is bijection okay, from x to x, and solutions are non-degenerate if this component map sigma x and tau y's are non-degenerate, and it's involutive if the solution square is 1. So there is a bijection between them. In fact, it's not very hard to check the check how this really happens. So if x is a cycle set, one can setting R of xy equals to this Lx inverse y dot x, where Lx is, recall, is the left multiplication with respect to the cycle set operation. This is a non-degenerate involutive solution of the Yang-Baxter set theoretic solution of the Yang-Baxter equation. Okay. And conversely, given such a solution, one can define a rack structure by setting x dot y to be sigma x inverse y. Okay, where sigma x is the first component of the solution. Okay, where yeah, okay. So here is written Rxy is sigma xy and tau ix. So sigma x is the first component of the solution. Okay. So now, okay, so we know that a special class of solution, namely non-degenerate involutive set theoretic solutions, are classified by these algebraic objects. So an attempt is made to classify these algebraic objects themselves, and in fact, a subclass of these objects. So to do that, we introduce this subclass first. So what is a linear cycle set? It's a linearized version. It's a cycle set with a little more richer structure, that you have an additional group structure, okay, which is an abelian group. We write additively here with this these two properties. Okay, in fact, you can deduce the cycle set axiom from these two. Okay, so one is left distributivity and other is the second one. So x plus y dot z is x dot y dot x dot z. Okay, and of course, if you take an abelian group and you just set each left multiplication by each element as just identity, that's obviously a linear cycle set. It's a trivial linear cycle set. And richer class of examples come from ring theory. So if you have an associated ring with unity and a right ideal contained in the Jacobson radical. So recall Jacobson radical is simply the intersection of maximal ideals for commutative rings, and it can be defined more generally. And if you have an ideal contained in this Jacobson radical, then by setting this cycle set operation A dot B as B into the unity plus A whole inverse, one can really turn this ideal A into a linear cycle set. So that's how there is a deep connection with ring theory. And in order to classify cycle sets, so let us focus linear cycle sets, it therefore become an attempt is to first know how to really construct new cycle sets out of the old ones. And one, as with any nice algebraic system, one has a cohomology theory, and therefore lead to extension theory. So that is what really happens here. So in order to classify all set theoretic solutions of the Yang-Baxter equation arising from cycle sets, it becomes essential to classify these objects. And therefore it becomes essential to understand extensions of these, which has subsequently led to a very nice cohomology theory for these algebraic systems. So I'm going to give a very special, very simpler version of this for our purpose to formulate the results in a simpler fashion. But there is a more general version of this. It's a very nice work of Leonardo van der Veen and Victoria Levitt, recent work rather. So rest of the talk will be around the cohomology of these algebraic systems, which give non-degenerate involutive set theoretic solutions of the Yang-Baxter equation. Yeah, so as I said, so this theory is developed in recent works of Levitt and van der Veen. I think the first one is an advances paper. The second one, I think is in Pacific Journal. Okay, so let us get into a little technical thing. So suppose you have two linear cycle sets. So you can just, at the back of your mind, you can think of it as a ring structure in mind, okay, to that there are two operations with some compatibility conditions, okay, and as an anamorphism is defined in an obvious way. So map phi from x to y is the morphism of in this category if phi of x plus y is phi x plus phi y, and they preserve the product also, okay, the rack product. And for any morphism, kernel we define as phi inverse of 0. One can talk about extensions of linear cycle sets, quite analogous to groups. Okay, so suppose there are two extensions of linear cycle sets, then what's an equivalence between them? An equivalence between them is an isomorphism from the middle one of one to the other, making this diagram commute. Okay, very similar definition as we see in groups. And so I will not define the general homology cochain complex. I will just focus on degree 2 for our purpose. So suppose you have a linear cycle set with multiplication dot and addition plus, and an abelian group, which for convenience we'll write additively. Then a two co-cycle of linear cycle sets is actually a pair of maps. It's a pair of maps from X cross X to A, satisfying these properties. Okay, so G of XY is G of Y plus G of X. There's some this co-cycle condition, and the third condition on F alone, and the fourth one, which is a mix of which involves both F and G. Okay, and one can see that condition 1 and 2 actually implies that G is a group theoretical two co-cycle. Okay, in fact, it's a symmetric two co-cycle because G of XY is G of YX. And here a two co-cycle is normalized if G of 0, 0 is 0, because once you import G of 0, 0 is 0, it will make similar assertions about F also. And two co-boundary can be defined also in a similar fashion. So if you have a pair of maps F and G from X cross X to A, okay, then it's a two co-boundary if there is a map lambda from X to A such that F can be written as F of XY can be written as lambda of X dot Y minus lambda Y, and G of XY can be written as lambda X plus Y minus lambda X minus lambda Y. Okay, so second condition you can see is just demanding that G is a two co-boundary, group theoretical two co-boundary. Okay, where the first one is a real one which really involves this cycle set operation. Okay, so one can look at the group of two co-cycles and group of two co-boundaries and take the quotient. That is what is the second cohomology of linear cycle sets with coefficients in A. Okay, so for example, if my operation is just trivial operation, X dot Y is just Y for every X and Y in set X, then I have just an abelian group. Okay, and I'm not doing anything new, so it is just the usual.
11 o'clock.
Sorry about it. So it's just the usual group theoretical group cohomology. Okay. So what Lebed and Ventramin observed is that if you have a linear cycle set and an abelian group and two maps from X cross X to A, then one can turn this X cross, this Cartesian product X times A into a linear cycle set with these operations if and only if Fg is a two co-cycle. So it's exactly is analogous to what happens in extension theory in groups. Okay, so if you forgot this dot operation, it is just exactly classical construction. Okay, so you can define sum of two elements as just add the two elements in the first component, the second one translate by the co-cycle. Okay, and similarly for the cycle set multiplication. So here we say an extension of linear cycle set is central if the dot multiplication by each element of the sublinear cycle set on the extension is trivial. Okay, so that the X dot Y is Y and Y dot X is X for each X in image of A and Y in this. So this in group theory, this is exactly how we can define if you just consider the conjugation action. And what they proved, Ventramin and Lebed proved, is that the set of equivalence classes of central extensions of linear cycle sets is in bijection with the second linear cycle set cohomology with coefficients in A. Okay, and these are the main this lemma is basically the main ingredient in the proof. And actually the proof of this is quite similar to what happens in groups. So one can just choose a set theoretic section, and then that section you consider the difference as we do in group theory. But in this case, we also do the similar thing for the multiplication. So there are some obvious observations here that there is a forgetful map from the linear cycle set to groups. In fact, the symmetric homology of groups. So because my co-cycles are symmetric with respect to the variables. So I denote the group cohomology by this notation just to distinguish. So there is this forgetful map. Okay, and in fact, that is something obvious, but more interesting is if you take the trivial linear cycle set, then the second linear cycle set cohomology is isomorphic to bilinear maps from X cross X to A times the second group symmetric group cohomology. So in other words, so for this actually classify this set on the right hand side, the group on the right hand side classifies meta-trivial linear cycle set extensions. So now toward the end of this talk, so let us build the notation for stating the main result. So I'm going to state a well-step exact sequence, and basically construction is very similar to what happens in groups. So suppose X be the group of linear cycle set automorphisms, and A with this line here be the group of group automorphisms, just to distinguish. So there is an action of this group on the second cohomology, very natural action set in this way. So on each of these maps F and G, you just define it in a very natural way. And let us set Z1, let us also recall this definition of the group of one linear cycle set cocycles, one cocycles. So these are mapped from X to A, which are group homomorphisms of the underlying additive group, and which are left multiplication invariant. Okay, so lambda X dot Y is lambda Y. Then one will be able to put them in this sequence. So suppose you start with a central extension of linear cycle sets and a two co-cycle of linear cycle sets, which induces that extension. And such a two co-cycle exists by Ventermin and Libet's result. And let us set this nice subgroup of the group of automorphisms of the extension E, the linear cycle set E. So which is those automorphisms which decompose like this. Okay, so psi of XA is phi X on the first component, and the second component it is lambda X plus theta of A, where phi and theta are automorphisms of X and A respectively. But there is this scaling factor here, lambda X, where lambda is just some map from X to A. Okay. Then one can put all the groups that I defined in this exact sequence. So you have a linear cycle set, and A an abelian group, E a central extension of this linear cycle set by this group A. In fact, when I say abelian group A, you can always view it as a trivial linear cycle set. So you can think that it's in genuine sense is a linear cycle set extension to a two co-cycle. So suppose E is an extension corresponding to the two co-cycle FG, then we can fit them in this exact sequence. So the linear cycle set, one co-cycles embed inside this group of automorphisms of the extension, and then there is a map from this group of group of automorphisms of extension E to this product X cross A, and the map you can see that is just mapping psi to phi and theta. Okay, one can ignore lambda, that is what happens. And then there is a very nice map from here to the second cohomology. Let us denote it by theta FG. Okay, and it turns out this is an exact sequence. So just in the last few minutes, comment about this map. So this map theta is not really a group homomorphism, but in fact it turns out to be a derivation. So you see that there is an action of X cross A on the second cohomology, and this map is actually a derivation. And in fact, if I change the cohomology class FG here, then how does this map change? Because if you just look at the last two terms, there is no extension E involved here. So it turns out that you do get a different map, but as derivations, they are actually cohomologous. So if you look at the cohomology of this big group, product group with coefficient in this, they actually give the same cohomology class. So in some sense, this map is very natural. And this is what the exact sequence of Wells type, because there is a similar exact sequence for groups. So therefore, this construction is very simple-minded. It's just more or less rewriting the same things. And moreover, the forgetful map from the category of linear cycle sets to the category of groups map this exact sequence for linear cycle sets to the corresponding exact sequence for groups. And in fact, that it's a natural map. Okay, so naturality is satisfied there. All right. So this, I think this is what I wanted to present. Thank you for your attention.
Okay, thank you very much. Very interesting talk. It really uses groups and quandle both. Yes. Thank you. So some questions, please. Yes, please. Camera is here.
Can you hear me?
Yeah, please.
Yes, yes, I can hear.
The first question, could you characterize the solution of the Baxter equation, which are related to the linear cyclic sets in proper terms as a solution of the Baxter equation? So it's involutive and it is linear, or what kind of other?
It's involutive and non-degenerate. So let me go back to that slide. Yeah, look, yeah. So cycle sets are, of course, non-degenerate involutive. So linear cycle sets also fall in this class. So yeah, I don't. So are you asking that whether linear cycle sets satisfy some more, some specific property? Is that the question?
No. Is it possible to characterize the solutions of the Baxter equation, which comes from the linear cyclic sets in proper terms, as a solution of the Baxter equation? What class of solutions you obtain?
What class of solutions?
Yes.
So they will give solution by this formula. That is one thing.
Okay. I have another more complicated question. How to generalize your construction in non-involutive case? For example, for the Hickey type solutions of the Baxter equation.
Yeah, I think one should be able to do it. In fact, similar construction we have, again, that's a work with Valery Bardakov. We could prove a similar exact sequence for quandles. Although quandles do not really behave like groups, but if you fix some base element in the quandle, one can do more or less similar construction. So yeah, I think one can do it for general solutions for which there is a nice cohomology theory. So basic idea of this Welch type sequence is that there should be the second cohomology should parameterize the extension, the so-called extension in that category, and then more or less one should be able to establish such a sequence.
And what about big bundles?
Biquandles, okay. So biquandles, is there? I don't know. I'm not aware whether there is a nice cohomology theory for biquandles. Yeah, I have not seen a cohomology theory. Nice cohomology theory for biquandles. Yeah.
Okay, thank you.
Yeah.
Okay, thank you. Please, are there more questions? No. So thank you very much for your talk.
Thank you very much.
Continue in 7 minutes. I'll give a small break. Татьяна сказала мне, что мне тоже можно попить чай по-прежнему.
Hi, Timur. How are you? Mahendra here. I think you.
structures. It's time to continue, and our next speaker is Manfred Singh. So, hello,
Hi, sir.
can you hear us? Can you see us?
Yes, sir. Yes,
Okay,
sir.
so please start. Please.
Okay. Thanks to the organizers for giving me the opportunity to present here. So I will speak about some properties of link quandles. Basically, I will talk about the residual finiteness and orderability property of quandles. So a quandle is a magma which satisfies three axioms. The first one is of idempotency. The second one is of bijectivity of right multiplication. That is, if we take any two elements in magma X, there exists a unique element Z such that X is Z star Y. And the third axiom is of right self-distributivity under the operation star. The axioms of quandle are basically minimal requirements for a magma to be an invariant for links in three sphere where we use the elements of magma to label the arcs of link diagrams, and there are some crossing relations at the crossings in the link diagram. So some natural examples of quandles arises from groups. So let G be a group, and we take any integer n, and we define an operation on the set G star H as H inverse n G H n. This forms a quandle and is noted by is known as n conjugation quandle. If we define operation of this type G star H as H G inverse H, then this is known as a core quandle. These are basically functors from the category of groups to the category of quandles. Now, if we take any subset of elements in the group G and a collection of subgroups of G such that each subgroup Hi is contained in the centralizer of element Zi, then the disjoint union of cosets of Hi in G forms a quandle under this operation. And these quandles are also known as coset quandles and are denoted like this. And the most important examples of quandles arise in knot theory. So let L be an oriented link in three spheres with n components. And we fix a base point x naught in the link exterior space. Now we define a set QL, which is a collection of homotopy classes of paths with initial point lying on the boundary of the link exterior and the final point at point x naught. And during the homotopy, we allow that the initial point can move freely on the boundary of the link exterior space. Now, if we define a binary operation on the set QL, say star, which is defined like this. So the diagrammatic interpretation of this operation I have depicted here. So suppose we have two elements A and B, and we define the A star B operation as we first move along the path A, and then we travel along the path B inverse, and then we go around the meridian at point B naught, and then we come back along the path B to the point X naught. One can check that this operation is well defined, and under this operation, this set QL forms a quandle and is known as link quandle. So one of the fundamental problems in knot theory is to list all links up to equivalence. Here by equivalence we mean we are talking about ambient isotopy of links. So it was proved by Matthew and Joyce independently around 1980s that link quandles are almost complete knot invariant. What I mean by this is that if K1 and K2 are any two oriented knots, then their knot quandles are isomorphic if and only if K1 is equivalent to K2 or K1 is equivalent to the reverse of the mirror image of K2. And this result was later on extended to non-split links by Fenn and Rudke. So as in case of link groups, one can write a vertical presentation from the link diagrams. There is a similar procedure to write a presentation of a link quandle from link diagrams. So the idea is quite similar as in case of groups. So let DL be an oriented link diagram of link L. Then we label the arcs of DL as x1, x2, xn. Then the link quandle is basically given by presentation, whose generators are basically the labeling of the arcs, and the relations are induced from each crossing by this rule. So here is an over arc A, which we have labeled with a symbol A, and under arcs B and C. And we add a relation C is equal to B star A, where C is lying on the left hand side of the arc A. So before going into the study of relatively finite quandles, I would like to say about this property in case of groups and how they are related to knot theory and in low dimensional topology. So we say a group G is said to be relatively finite if we take any two distinct elements in the group G, and we can find a finite group and a homomorphism from G to F such that the homomorphism can distinguish the images of the two said elements. It is well known that free groups are relatively finite. Moreover, Newitz proved that the knot groups of all fiber nodes are relatively finite. Moreover, Newitz conjectured that the same is true for all link groups. And later on, by the seminal work of Hempel and Thurston, it was established that all link groups are relatively finite groups. Moreover, as a consequence of Perriman's proof of geometrization conjecture, the fundamental groups of all compact three manifolds are known to be relatively finite. Now, analogous to groups, one can define relatively finite quandles. So, a quandle X is said to be relatively finite if for any two distinct elements in quandle X, there exists a finite quandle and a homomorphism such that the two images of two elements are distinct under this homomorphism. In joint work with Professor Valerie Bartkov and Professor Mahinder Singh, we proved that all link quandles are relatively finite. I will briefly sketch out the proof of this theorem in the next few slides. So let L be an oriented link with n components, and SI hat be the map induced on the level of fundamental groups via the inclusion of boundary components in the link exterior space. And we denote the image of SI hats by HI, which are known as peripheral subgroups. And these are abelian groups because the left hand side on this is basically abelian group. It is basically a direct sum of two copies of integers. It was proved by Matthews and Joyce that the link quandle has this representation. We will exploit this representation to prove that the link quandles are basically relatively finite. So here HI is a peripheral subgroup for each component. Pi 1 CL is basically a link group, that is a fundamental group of the link exterior space, or one can say a fundamental group of link complement space. Here MXI denotes the image of the meridian at point x naught, xi under the map SI hat. Now let G be a group and H a subgroup of G. Then H is said to be finitely separable in G if for any element G in the group G which is not lying inside subgroup H, there exists a finite group and a homomorphism from G to F such that the image of element G does not lie in the image of the subgroup of H under the map phi. Note that this is basically extension of the relatively finite groups. In particular, if we take H to be an identity element, then this definition is basically of relatively finite groups. We show that if each HI is finitely separable in the group G, then this coset quandle is basically a relatively finite quandle. Moreover, Long and Niblo study the finite separability of fundamental groups of boundaries of three manifolds. In particular, they prove that suppose that M is an orientable, irreducible compact three manifold and X an incompressible connected subsurface of a component of the boundary of M. Then the fundamental group of X is finitely separable subgroup in the fundamental group of manifold M. Now, if we take a non-separate link, which is not the unknot, of course for unknot, there is nothing to prove about the residual finiteness. So let's suppose we take a non-separate link, which is not the trivial knot. then it satisfies all the conditions of this result, that is the link exterior is orientable, reducible, complexly manifold. But then by this result, each peripheral subgroup is finitely separable in the link group. And by this result and the previous result of Matthew and Joyce, where they have presented the link quandle as coset quandle, we recover that for non-split links, the link quandles are basically residually finite because each peripheral subgroup is finitely separable. Now we are remaining with the case of split links. For split links, we need to study the property of residual finiteness under the free products. I would like to comment here that free quandles are residually finite as they are actually sub-quandles of conjugation quandle of free groups, and free groups are known to be residually finite. Now let Q be a quandle, then the enveloping group associated to quandle Q is defined by a presentation as given below. Here the generators correspond to the elements of the set of the quandle Q, and we have relations of conjugation. Note that there is a natural map from quandle Q to its enveloping group, and this map is basically a quandle homomorphism if we look at the enveloping group as a conjugation quandle. Moreover, there is a natural right action of the enveloping group on the quandle Q defined like this. We prove that let Qi be a family of residually finite quandles. Assuming that the enveloping group of each Qi is a residually finite group, then the free product of these quandles is a residually finite quandle. Now, if we look at split links, then one can easily observe that the link quandle of split link is basically a free product of quandles corresponding to the non-split components. So if we can somehow prove that the enveloping group of link quandles of non-split links are residually finite, then we are done by this theorem. And this actually indeed true by the result of Matthew and Joyce, where they have proved that the link that the enveloping group of any link quandle is basically nothing but the link group, and link groups are known to be residually finite, and hence this completes the proof. Now I will move towards the second property of link quandle, which is orderability. But before that, I will say something about this property in case of groups and how they are related to low-dimensional topology and knot theory. A group G is said to be left orderable if there is a strict linear order on G, which is invariant under the left multiplication. Similarly, one can define right orderable groups, and by bi-orderable groups we mean that there exists a strict linear order which is invariant under both left and right multiplication. Some examples are basically free groups are known to be bi-orderable groups. Fundamental group of connected surfaces except the projective plane and the Klein-Bortle are bi-orderable. In knot theory, the braid groups are known to be left orderable, but braid groups on more than two strands are not bi-orderable. Moreover, it was proved that link groups are left orderable groups. So the natural question is now, of course, one can easily see that we can define the orderability for for quandles. The question is, what can we say about the orderability of link quandles? So we say a quandle is left orderable if there is strict linear order, which is invariant under the left multiplication, and similarly one can define right orderability. And we say a quandle is bi-orderable if the linear order is invariant under both left and right multiplication. Some examples are, if G is bi-orderable group, then its conjugation quandle is right orderable. Its core quandle is always left orderable. Moreover, the conjugation quandle of any group can never be left orderable, and similarly the core quandle of any group cannot be right orderable. So here is something important to note here, that unlike groups, left orderability or left orderability in quandles does not imply right orderability in quandles, and vice versa also. Recall that we have seen that there is a natural map from quandle Q to its enveloping group, which is basically quandle homomorphism. Here is an interesting observation. So let Q be a quandle. And if we assume that the natural map from quandle to its enveloping group is basically injective, and we also assume that the enveloping group is a biodrable group, then the quandle Q is basically a right-orderable quandle. This one can easily check. Now it was proved by Perrin and Rolfson that if all the roots of Alexander polynomial of a fiber knot are real and positive, then its knot group is biodrable group. Now if we add the primeness here, that the knot is also prime knot, then one can easily see that the knot quandle is right-orderable. The main idea is that for prime knots, this map, eta map from quandle Q to its enveloping group is always injective. And thus, for prime knots, if we add the condition of prime knots here, then they are basically, then their linked quandles are basically right-orderable. Sorry, not quandles are right-orderable. Now, in joint work with Dr. Hidesh Rondal and Professor Mahinder Singh, we study the orderability of torus links for some special cases. So let m and n be two integers such that they are not multiple of each other. Then we prove that the link quandle of torus links is not right-orderable. I will sketch the proof of this in the next few slides. But before that, let's see its straightforward consequences. It was proved by Perrin and Rolfson that the knot group of non-trivial torus knot is not biodrable, and this result can be recovered from this result by noting that the torus knots are basically prime knots, and for prime knots the link, the knot quandle, the map eta from knot quandle to its enveloping group is injective. We also prove that the knot quandle of the trefoil knot is neither left orderable nor right orderable. Thus, we have examples of knots where their link quandles are right orderable. We have examples where they are not right orderable, and we have also an example where the knot quandle is neither left orderable nor right orderable. So here is a brief sketch of the proof. So let tau mn denotes the stack of n copies of the storic bread tau mn 1, and we take the closure which gives us torus link tmn. Now one can easily check that the link quandle of torus links have a presentation where the generators are a1, a2, an, and these are the some relations. It was proved by Rost and Jashin that by assuming that m is less than or equal to n, the elements EA1, EA2, and EAN, these are basically generators in the link group of torus link tau mn. These generators are basically distinct in the link group. So we will need this result. The thing is that if these are distinct generators in case of link groups, then A1, A2, and AM are also distinct in the link quandle of this torus link because of the natural map from quandle to its enveloping group. So here is a brief sketch. Suppose the link quandle is basically right-orderable with some linear order. These are basically relations as we have seen in the previous proposition, and one can deduce these two identities from this one. And by the result of Rost and Jashin, these are A1, A2, and AMN are not equal to each other. Now assume D is basically a GCD of M and N. Since M and N are not multiple of each other, and we have assumed that M is less than N, we have D is strictly less than N. And since there is a linear order, we can either A1 is less than or greater than AD plus 1. Now one can note that the action of the enveloping, noting that under the action of the enveloping group, the right order remains preserved, and by repeatedly using the second and third identity, we have these inequalities, and one can easily, from these inequalities, one can easily prove that the A1 is not equal to A1, which is basically contradiction, and hence the link quandles of torus links where M and N are not multiple of each other, they are not right orderable. We have also studied the orderability of alternating links. In particular, we have proved that let L1 be any link and L2 a non-trivial positive link. By positive link, we mean that there is a diagram of link L2 where all the crossings are positive. Suppose there exists a minimal positive diagram of link L2 such that the generators in the presentation of the link element QL2 are distinct. Then we show that the link quandle of connected sum of links L1 and L2 is not biodrival. In particular, this implies that the link quandle of L2 is not biodrival. So here is a brief sketch of the proof. I will basically prove the last part, and another part is basically the extension of it. I will basically prove that the link quandle of QLT is not biodrival. So let D be a minimal positive diagram of link L, and such that all the arcs in D are correspond to distinct generators. So we have a presentation of QL, quantum QL. We take a set of S, which is of generators corresponding to the arcs in the diagram of D. And since assume that the quandle QL is biodrival, there is a linear order, there is some linear order, and thus we can assume that there is some minimal and maximal element in the set S under that order, say y1 hat, y2 hat. It is easy to note that one can actually find a crossing where y1 hat and y2 hat are basically the outcoming under arcs. Now, since D is minimal, and we have assumed that all the generators are distinct, one can easily deduce that Vi hat is not equal to Ui hat for I equal to 1 and 2. And since D is positive, we have assumed that, and QL, we have also assumed that QL is biorder under some order. One can actually check that either this is satisfied or this condition is satisfied, which is basically a contradiction to the minimality or to the maximality of y1 hat and y2 hat respectively. And this completes the proof. That is this quantity is not biodrival. So here are some state consequences of this result. So it was proved by Mattman and Solis, proved the Coffin hierarchic conjecture, which is as follows. Let D be reduced. By reduced diagram, we mean that there are no crossings of this kind. Okay. So let D be a reduced alternating diagram of a node K having prime determinant. Then Mattman and Solis proved that every non-trivial P coloring of D assigns different colors to different arcs in D. By P coloring, we mean that quandle homomorphism from the node quandle of K to the core quandle of cyclic group of order P. Okay, and basically what they have proved that if the homomorphism is non-constant, then every arc in the diagram D can be labeled with distinct elements with the core quandle of the group cyclic group of order P. Now, if we add the condition that this alternating node is basically a positive node, then one can easily, using our previous result and this result, one can easily check that the node quandle K is not biodrival. Basically, this axiom ensures that all the generators in the diagram D are distinct, and this is where we have used it. And one last consequence, the Coffin hierarchy conjecture was later on extended to another conjecture by Asida, Prisky, and Sikora, which is now known as generalized Coffin hierarchy conjecture. The motivation behind extending the Coffin hierarchy conjecture is that the determinant of a node is basically the order of the first homology group of the double cover of three sphere branched along the node L. And this is noting this, they introduce a more generalized version of the conjecture. That is, if D is an alternating diagram of prime link L with no negatory crossings, then the different arcs of D represent different elements of the first homology group of double cover of three sphere branched along link L. And this conjecture was also confirmed for the Montesinos link by Asida, Prisky, and Sikora. And again, if we add one more condition that the non-alternating Montesinos links are positive or say negative, then by our previous result, one can ensure that the link quandle of M is not biodrival. And with this, I finish my talk. Thank you.
Thank you very much. Any comments, questions, if any? I have a question related to manifolds. So you mentioned about the conjecture about twofold branch covering of the rings. What about other secret branch coverings? Do you know something?
Sorry, can you please repeat the question?
So you present conjecture by Pshititsky about double cover of the cell branch cover of a leaf. And if you consider not twofold branch cover, but for example, any secret and fold branch cover of the leaf, do you know something about this? I mean, other similar conjecture, other similar results in this case.
Sorry, I don't get the question actually. But this conjecture is only proved from Tyson link. I know that. The idea behind this conjecture is that so in the Coffin hierarchy conjecture, the main thing is that they have assumed that the determinant of the node is basically prime number, and this is the main thing. And they Sita Priestley and Sikora noticed that the determinant can be recovered from the first homology group of double cover of 3 sphere, and so they extend their conjecture to the to links using the using this group. Basically, they don't basically they don't only use this quandles. Basically, the quandles are obtained from the core quandle of cyclic group of order P. They actually increase the domain of the coloring basically here.
Okay, thank you. More questions?
Thank you.
There are no questions. Thank you again very much. Thank you very much. And we have a lunch now. So we'll come back at 3 o'clock. Thank you very much to everybody. Значит, у нас есть сколько получается сейчас?